When you start building your robotics software, you find out input to your software is mostly robotic sensor data. In software, you do the processing, you generate as an output a control signal for your robot. Now, the middle part, the software that you write, you are responsible for it. And you find out that there are a lot of libraries involved in it. For computer vision, OpenCV, for path planning, OMPL, for understanding 3D environment, it's PCL, and AI, PyTorch. Now, in this whole scenario, you need to understand without confusion how to bring these libraries into your software. If it's Python, if it's C++, you should be very clear. But I understand most of the people are not. So this video is for those people to understand from basic software and also with ROS2 simulation, how to add libraries into your software stack. Let's start with adding OpenCV in Python. First, we need to install OpenCV. You simply write install OpenCV and it gives you install OpenCV for Python. For Python libraries, it's very easy to simply install things with this pip Python package manager. Let's simply paste this command and it is going to install your OpenCV for your system, specifically for Python. Now, to utilize it, you need to write some code. I have already created a basic structure for this Python script, a basic Python script, OpenCV Python. What it does, it says import CV2. And I provide the path to the image that I have, humanoid robot, which is a simple image of humanoid robot. What we are going to do is to load this image into CV2 by providing the path, then applying the grayscale conversion. And once that is done, simply display the actual image and display the grayscale image. That's it. So we can test that our library is currently working. Make sure the path to the image is correct, then you can simply run this. You go into the exact location where the file is, which is in this directory. So python3 opencv.py. This is going to bring up two images, one actual image, one grayscale image. And quite interestingly, it displays. You can zoom in and find out the RGB values at each pixel as well. This was OpenCV. Our OpenCV is working. We need to now move to PyTorch. Adding PyTorch in Python. First, let's install PyTorch while going to its official website. And here we are going to start locally. Our PyTorch should be stable, operating system Linux, package pip, Python, and I'm going to go for CPU install, not GPU. So this command has to be copied and simply pasted to my terminal. Make sure that you are pasting these commands into your specific environment, not system-wide installation. If you don't understand this, leave this instruction. For now, just install things to understand how you can utilize different libraries. PyTorch is installed theoretically. Let's test it. This is a script that I have created and it imports Torch, PIL library for image processing, and Torch Vision Model ResNet. This is the default model baked into Torch that we can utilize. I have provided the same image that we saw earlier and it is converted to RGB. Let's write some code starting with loading the weights of the model from PyTorch itself and loading the model in evaluation mode. Next, we need to build the exact pre-processing from the weights that converts PIL image and adds a batch dimension. Afterwards, we run a no-grad forward pass to get logits in a desired form. At the final thing, we convert those logits and turn them to class of probabilities that we will log and find out what is the maximum probability for this image. Run this by python3 pytorch, press enter. When you're running for the first time, it is going to take some time for downloading the weights. In my case, it says it's a tripod with 43% confidence or probability. So our robot is actually not a tripod, but let's just focus on to the thing that we were trying to do, understanding the library, installing and running on your system. Now coming to C++. This is going to be complicated because it's not similar to Python. In C++, you will observe that you have to include headers, you have to add things into your CMake list and produce binaries, which is complex for starters. But when you get into C++, you find out that this is very powerful to work with and efficient as well. So let's understand how we can add very important library of point cloud processing, PCL, and then OMPL, Open Motion Planning Library. Running PCL with C++. Starting with PCL library, it's very important library for robotics, as much as important as PyTorch for AI, because it deals with the depth data processing in C++. It's quite efficient. It utilizes the best libraries of C++ available for computations. Now you can see in self-driving car, it's all depth clouds in most of the cases except Tesla, but in other robotics applications there is as well. Install PCL, and it's quite simple, similar to pip installation style. It directly suggests for Linux you perform sudo apt install libpcl dev. Once you have installed, we need to test this installation, and for that, once you have installed it, you are going to check your installation. And how do you do that? You list user include. This is the point where things are installed. I write PCL and press double tab. It provides me PCL 1.2 and it automatically completes on pressing tab, which means that library package is available that I can include and its headers are available. So let's write a basic script in C++. It's a pcl.cpp file that includes point clouds and point types out of this available library package. So if we check PCL, and it's calling point clouds.h. This is the header file available inside of this user include, which we are accessing here. Let's write the very basic form of code by creating a container by using this PCL template of point xyz and add a 3D point with x1, y2, z3. That's it. It's simply using a function to create a point in 3D space. That's it. Now to run this, things are going to get different as compared to Python, which is the main reason people don't like C++ in the start, because it's not that direct and easy. By just pressing Python or just running it, it is going to run. You need to perform certain settings. For example, for this specific one, if I write G++, the compiler, and pcl.cpp, the script that we have, I want it to output an executable named as PCL. This is the executable, but if I press enter, it's going to give me an error that where is this file? Although we check that this is available in our system, but we have to provide the path to it, unlike Python. So -i represents include, user include PCL 1.12. That's what we have installed. Press enter. Now you will observe that the error has changed. So it has found point cloud, but this time it says eigen is unavailable. So similar to PCL, we have to install eigen, and you just simply do that by install eigen linux. It's simply this command because eigen is header only, and it is very useful for performing computations, and most of the popular libraries utilize eigen in their workflows. Similar to this, I have to provide the path for eigen, user include and eigen3. Press enter. This time I provided manually the path, and it produces the PCL executable. Executable can be ran through ./PCL, and it says PCL OK, meaning this library is also now working. So this is the basic working behind the scenes when you are running and trying to utilize a library. Running OMPL with C++. The last library we will be looking at is OMPL CPP, which is for open motion planning, and it creates path inside of point clouds, and it's very useful library. So how do we test it? We created some namespaces. The simplest code we are going to write is allocate a 2D real vector state space and a bound object. Then we set both the dimensions bound to -1 and 1, apply them to the space. Then we set the bounds. At last we just say OMPL is now working. So this might not make sense right now, but it will when we will look at in the ROS2 simulation. For OMPL, I will use a little different process to compile. Although it's going to utilize G++, OMPL.cpp, output into an executable of OMPL, but this time utilize package configuration of OMPL, which we did not use for PCL, and there are a lot of other options that we can do with these libraries as well. Let's run OMPL, and OMPL is also working. So PCL, OMPL, PyTorch, OpenCV are working with standalone scripts. Let's integrate into ROS2 and understand how things are different there. But the basic understanding is the same. This line actually brings in multiple paths that automatically gets included and are related to OMPL. That's why this $sign is used, and we include all of those directly into our script. So things become easier. That's why we use this approach. Let's now move to ROS2 simulation. Till this point, you now understand how to add libraries into C++ or Python software. Now it's time to understand how to bring it into ROS2 ecosystem or libraries into your ROS2 packages so you can extend your functionality, as sensor data is enormously available and easily accessible in ROS2. So let's start with Python. For ROS2 simulation, we are going to be using this JAMP library by CHVMP, which contains MIT cheat and other robot dogs that you can simulate in ROS2. I have created a clone of this repository. You can go through this repository. It's an amazing repository with a lot of navigation and other scripts that you can run. In our scenario, we are going to be cloning it, and I would suggest you to copy and paste these commands. So clone it, recursive install all the dependencies, coming to the point where you have call can build it successfully and run this jamp config gazebo.gen.launch file. Let's visualize it. Source install setup bash and then launching this gazebo simulation. It contains the ROS and gazebo simulation. In our scenario, we need to look at multiple things. The sensors we are interested in, starting from the camera, have placed something in front. The camera tells us that this is the current updated freed from camera sensor. Depth points is one of the most important things that we are interested. It's 3D point cloud data available to us from the depth sensor, which is on top of it. Let's bring another object to see if it's updating or not. So everything is working fine. For OMPL and PCL, we need two data lines, the camera feed and point cloud. We will then later on process these. So what I have done, I have already cloned this JAMP directory and created this new package, JAMP library integration, which contains source files and which contains CMake list. Let's now work on this OpenCV PyTorch, and this is going to do multiple things. Run OpenCV node and also the PyTorch thing for detecting what is in front of the robot in the form of camera feed, not the depth one. So this is Python based, including both of the libraries. As we have already done in a very simplistic way, OpenCV was OpenCV2. Just importing that. In our scenario, it is imported there. And for PyTorch, it was import torch. Here we can observe import torch and PIL image is also included. But the way things are working is different because ROS2, which adds up messaging layer on top and node subscribe and communicate with those messages. That's why we have a structure of the node, and for executors, callbacks, our ROS2 ecosystem is there. But if you understand object-oriented practices through Python, you can understand what this code is doing. Importing the libraries, creating a class. Class is inherited by this node class that ROS2 Python provides, ROS_Py. And what it does, it creates a bridge in between OpenCV and ROS camera image. Other than that, there is a subscriber to get the image, publisher publish gray image, and AI label that outputs what PyTorch predicted. Same things as we did in the simple Python script of PyTorch. This callback is what we are going to work on. Till this point, we are getting an image, converting into gray. Next, we want is to publish this gray image. Simply self.publish gray image and publish through the bridge by converting it so we can visualize it. Next up is this RGB CV object that we obtained to process image for PyTorch. We then create a PIL image. Then the same torch no grad functionality pre-process the image and bring it to the size that we want. So Logits can produce an output and we can calculate the probabilities of it, and similar to the previous operation, log out the maximum value category that we have in the list. Afterwards, just publish this label onto ROS2 topic. Python was quite easy. We just added executable path and that's it. Now coming to C++, we need some extra steps to tell where the library is, where to put the executable file, and what to link when generating an executable. Let's look into that. Let's create the OMPL and PCL node. Again, a lot of libraries and headers are already included of OMPL and PCL. I have combined OMPL, PCL in one node and OpenCV and PyTorch in another node. Similar to the previous structure, node is inherited. Class is created by inheriting the node RCLCPP node. Then subscription on the depth points is created, and now we are going to write the callback function for the cloud. It's going to do a lot of things. Let's start by first creating a container of XYZ point in 3D space. Then we create a message and copy the contents of input message that we received to this callback. Then we created a voxel grid. Set input to the input cloud, creating voxel size of 10 centimeter, and then save this into another container as an output. Then we say filter this new container. Once that is done, we simply log this information that we obtained this much of an input of point cloud, and we reduce the size of it. Coming to the next thing of OMPL testing the library, we are first going to create a space of 2-dimensional. Then we create bounds to it starting from -1 to 6. Then we apply those bounds to the space. Define that this is going to be a simple setup and apply the validity checker, although we are ignoring the obstacles for now. Setting the start point in this space 0, 0, and the goal point in this state is going to be 5 in X, 5 in Y, and then apply these points to the state. Now comes the OMPL get solution function, which takes inputs and time, then replies with the result that if it has produced a plan in these constraints or it has failed. This is going to be simple ROS log. Although there is not much happening and not actual functions are called properly, but still I just wanted to let you experience that how you can work with the data from ROS2 with these libraries. Now comes the most important one, and that is related to compiling. As one node was C++ related, so we have to add the executable into it, then target include dependencies of PCL, and then linking the libraries of OMPL. Afterwards, ROS dependencies that we will be using are RCL, sensor messages, and PCL conversion. Once all of this is linked, then we install it into our package shared directory so we can access it easily. All the setup seems to be ready. Let's compile it. Call can build. Apparently it seems to be working fine. Let's run the simulation, bring another terminal, and we are going to run first a basic OpenCV and Python related output. We are going to check that first. I'm going to place in front of it a cube. I don't know if ResNet has this category in their training data. Apparently there is one cube. So let's call this node ROS2 run. We need to first source it. ROS2 run champ library, and the nodes we have OpenCV and PyTorch. Press enter. So it is running. We need to look at the topics that it is publishing. ROS2 topic list. The one we are interested and we were publishing on is AI label. Let's run that. ROS2 topic echo AI label. It should be publishing a text message in front of it. It says it's a loudspeaker. Also, there should be a topic to just grayscale the data. It is named as image gray. It's already grayscaled. If I put something of a ball in front of it, what does the model says? It says Caldron. Okay. So the model is basically working and it's changing its output based on whatever understanding it has. Now it's a puck. If I just move it back, it's a ping pong ball now. Perfect. So PyTorch and OpenCV integration is working perfectly. Let's disable this. So this is a complex C++ node, and apparently for people who are starting out with C++, these templates don't make sense, right? But bigger libraries are arranged in that order. You will get the code, it's available in the GitHub. Things that you need to understand in the basic structure, what I have done, I have added these 4 lines specifically to publish out the output of the PCL. Although OMPL, we are not visualizing it. Otherwise, a lot of code has to be added and you might get bored of it, that's why I'm not adding it. But simple output of OMPL is going to be logged, and the logs will contain the information about what it computed. We have the simulation in ROS. In front of the robot, we are going to place some objects at a far distance. I have increased the depth sensor parameters so we can actually see at a far distance. If I put these objects here and we enable the depth points, we can see we have some objects, and we can go far beyond this to have more objects as well. Let's put something far away. Yes, we have that. Let's run the node for this OpenCL ROS2 run jam libraries integration and PCL. So it has started to perform certain operations, some blue lines and some green lines, and there is a log also there. Let me scroll up. You will find out that something downsampled cloud is written and no planner certified. There it is obtaining certain specific planner configuration, and some goal is found as it is logged. But let's understand what is happening. This is a quite heavy on CPU simulation because a lot of points are there. The total points in this point cloud that we can visualize are 307,000 points that we are reducing to just 2,200. So that's a big reduction in size of these point clouds. Let me add that point cloud that we are producing after reduction using PCL library, and you will find out why this library is very important when processing depth point cloud data. So if I disable depth points, you will see very tiny small points that we are obtaining, and the simulation is now very smooth. The reason is that this is the reduced points, reduced features of the actual data that we were receiving from the depth sensor, although in simulation. But one thing to understand, you can see the structure is the same, and we can process the path planning in between it, and we are doing it. That's why the OMPL is logging thing. Now what this is actually telling us about, if we scroll up to the point of reduction, for now I'm just running very small operations of downsampling the cloud, meaning reducing the number of points and taking an average in this node that you can observe here. You can further reduce it. The size is going to reduce, the number of points are going to reduce. But what is important is with this small points, we can still able to find the path, because OMPL found the path starting from the origin point, which is 00 to 55, which is 1, 2, 3, 4, somewhere here. It has been able to find the path, although there is an obstacle on it, but we have disabled obstacle avoiding and made it very simple for you. You can add more functionality to it. The main purpose of this whole process was to make you understand how to add libraries into basic scripts and ROS2, which has been achieved. The libraries we used are the 4 day-to-day important libraries in robotics. When you want to see the world through camera, it's OpenCV, computer vision. When you want to process the 3D data of point cloud, it's PCL, point cloud library. And OMPL for path planning of robot in 3-dimensional data, also PyTorch for AI extension into your robotics. So these are very important, but as a software developer of robots, you need to understand one very important thing. Sensors are going to be the main input to your robot. You are going to write a software, and that software is going to produce an output, mainly in a control signal or driving command for the robot. That's it. So software comes in the middle, libraries come on top of that and makes your life easier, and you can build good data processing pipelines with those libraries.